I'm Andrew Katz, Joint Managing Partner and Head of the Technology Law Team at Moorcrofts. And my specialism is open technologies. I've been advising on open technologies for more than 20 years, and this covers not only open source software, but also more recently open data and open hardware. Open hardware is a very rapidly developing field, and in fact I was asked to lead a study into open hardware as part of a broader study on open source software and hardware, which was initiated by the European Commission. And that, as of we're currently May 2021, and that has now come to the final stages. We've submitted a final report, which hopefully will be published shortly. To understand open hardware, the best place to start is probably to think about open source software. So what's open source software? Well, open source software is software that is available under a license that enables you to use it, to study it, to modify it, and then to distribute it, either with or without your own modifications, freely, without any restriction, apart from some restrictions, which might be, for example, you have to retain copyright notices, or possibly you may have to distribute derivative works of that software under the same license. So open hardware is very similar, except rather than talking about software, we're talking about hardware, and rather than talking about source code, we're talking about the design materials. So open hardware is hardware whose design materials are made freely available. Anyone is allowed to make that hardware, anyone is allowed to modify the design materials, anyone is allowed to distribute that hardware. And again, there may be some restrictions on the extent that you can do that, so you may have to retain attribution notices, copyright notices, and so on. And if you do make any modifications to the design materials, you may also have to ensure that what you're distributing is distributed under the same terms. It's probably not helpful to get bogged down in the differences between open hardware and open source hardware, because there have been a number of attempts to define both of those terms over the years. So probably the best place to look is the Open Source Hardware Association's definition, which really does a pretty good job of combining the two best known definitions of open source software and free software, which exist in the free and open source software worlds, and then turning them into a definition for open source hardware. But essentially, it's what I said. It's hardware that's made publicly available. The design materials are available for use, modification, and redistribution. Well, by hardware, we can mean a very wide range of things. So we can mean everything from cars to drones, to electronic circuit boards. Beer has even been made available as open hardware. But most commonly, we're probably talking about electronic devices. And these can be electronic devices at the circuit board level, but also at the chip level. And one of the most interesting areas of development for open source hardware at the moment is open silicon. One of the most interesting developments in silicon chip technology has been the invention of the FPGA. So what's an FPGA? Well, it's a field programmable gate array. And what this is basically, it's like a blank canvas. Now, if you take a normal piece of silicon, a normal silicon chip, and they're typically designed to do various functions related to logic. So they consist of a bunch of components within them that are typically logic gates, so AND gates, OR gates, XOR gates, and larger components like buffers and so on. And then these are combined, and they're combined in a way that can enable you to make a microprocessor or a memory chip, or some special function interface chip like a RAM interface, or a UART or so on. So these are chips that are designed for one function. Now, it may be that they're very versatile, and that, like a processor, for example, you can obviously program a processor to do very many things, but the processor does those things by reading a sequence of instructions that's external to it. An FPGA, by contrast, essentially is a blank canvas that enables you to configure it to contain any sort of set of logic gates combined in whatever way you want up to the capacity of the chip. So this means that you can configure an FPGA so that it can become a memory chip, or it can become a processor, or it can fulfill any number of different purposes. And once you've done that, it's not fixed. You can reconfigure it to do other things. And this provides unparalleled flexibility, but it also means that it's great for testing. So the opposite of an FPGA is an ASIC, which is an application-specific integrated circuit. Now, almost all integrated circuits that exist out there are ASICs. They're designed for one particular function only. To configure an FPGA, you need to decide what functions it's going to have and which logic gates you need to use in order to configure it. And rather than drawing out a set of logic gates in a sort of circuit diagram, what is typically done these days is to use something called a hardware description language, such as Verilog. So a hardware description language, to those who are familiar with computer software languages, looks very, very similar. But they're not functional. They do not go through the process step by step in the way that you would with a normal computer software language. What they do is they describe the functionality of a set of logic gates in a way that once those set of logic gates are configured, that they essentially themselves become a silicon chip. So, for example, it is possible to describe a microprocessor unit using simply a hardware description language like Verilog. And then it goes through a tool chain, which is similar to the sort of tool chain that you'd have in the software world of compilers and linkers, to create what's known as a bit stream. And a bit stream is the binary code that will be fed into the FPGA that will automatically load at startup, and that will configure the FPGA, and the FPGA then essentially becomes the chip that you want it to be. So RISC-V is an instruction set architecture that was developed in the University of California at Berkeley. And an instruction set architecture is basically, it's the set of instructions that you need in order to program a microprocessor. And the great thing about RISC-V is that the architecture was made freely available under very, very permissive license. So it means that anyone can take the RISC-V instruction set and they can implement a microprocessor design. And indeed, there have been many microprocessors that have been developed which make use of this RISC-V architecture. No, not by itself. RISC-V is not open hardware. It's just an instruction set architecture. But it has led to the development of a number of open hardware microprocessor cores based on the RISC-V architecture. So they include things like Swerve, Low Risk, and so on. And all of a sudden, it's possible for people very easily to take these components and then build them into more complex devices, whether it's Internet of Things devices, whether it's special purpose processors for using cars, for example, based on these building blocks. And this really is an area of great interest for open hardware developers. In this context, no. We talked a bit earlier about the development process for open silicon, and it typically involves writing in a hardware description language that looks very similar to a computer software language, and a lot of the similar infrastructure can be used. So you can design your code using an infrastructure like GitHub or GitLab. People can contribute to it in the same way. So a lot of the mechanisms that people associate with open source software development, the ability to have distributed developers, the ability to be able to communicate with each other over distance using the internet, the ability to be able to test early, release often, many eyes make all bugs shallow, all of these ideas that apply to open source software, they apply to the development of open silicon for FPGAs in the same way. So the design, test, fix cycle can be very, very rapid with FPGAs, in the same way as it can be with open source software. So there are a great deal of similarities there. However, as we said earlier, hardware is something that is much, much broader than just talking about open silicon. So if you're talking about an open source dump truck, for example, then you can't really design a dump truck effectively on GitHub, because ultimately you've got to turn this thing into something physical, and to do that you've got to have a factory, and the factory has to be full of things like lathes and milling machines. It's very expensive, needs a lot of energy, a lot of equipment. So this is completely different from the sort of environment that you have when you're designing open silicon, which you can do on a very inexpensive piece of computer equipment. And as long as you have internet connectivity, and most of the toolchain components, in the same way as they are for open source software, are available in some form in open source form themselves. Now, this is potentially a big problem, and I'll get onto that in a second. But at least in theory, it's possible to design in very much the same way if you're talking about open silicon. And then you've got other sorts of design in the middle, such as design for design for PCBs. So PCBs can also be designed using GitHub, for example, in a very digital domain sort of way. And also, it's pretty quick to be able to get a physical PCB in your hand. Even if you're not making it yourself, there are services available where you can send the files off to a company, and there are many all over the world. There's likely to be one local, relatively local to you. And then they can manufacture this thing and they will send it to you, and within 24 hours, if you pay for an express service, you can have a physical PCB in your hand. Again, that's not the case with dump trucks. You're not going to be able to get somebody to 3D print a dump truck for you in 24 hours. So the cycle of design, build, test varies depending on the type of open hardware that you're talking about.
Well, I think we touched on one of the challenges earlier, which is the question of the tool chains. And one thing that has been very clear from the world of open source, and it's now almost become just an accepted part of the world, is that many of the best tools, if not all of the best tools, are available themselves under open source licenses. So GCC, which is the GNU compiler collection, that is a world-class standard for compilers. Then you've got IDEs like Eclipse. So all of the tools that you need to develop software are available freely, free of charge. So to get started in the world of open source software development and to be able to participate in open source communities and to communicate with other people in those communities, and to be able to create software that's on a par with the sort of software that any large organization is going to create, at least in theory, is possible with a very low barrier to entry. You need a fairly basic PC running the Linux operating system, which is free, using these various tools, which are free. You need internet connectivity, but once you've got a reasonable speed of internet connectivity, then you can make use of GitLab, GitHub, all the other sort of communication mechanisms that people have to create open source communities and develop open source projects. Much of that is also true of open silicon design, but the one area where things are lacking at the moment really is in terms of the tool chain. So open source tool chains and tools are coming onto availability. They're being released. Increasingly, there's an increasingly large number of them, but still many of the top end tools are still proprietary, and that can provide a very large barrier to entry. Another challenge is around standardization. One issue that we have at the moment is that a lot of the tools are fairly specific to individual vendors' FPGAs, which means that it's not necessarily that easy to transfer code that you've developed for one FPGA to another FPGA. So in addition to the potential costs of buying the tooling in the first place, that does produce a barrier to switching. It does produce a sort of form of lock-in, and that in itself can be problematic. Well, Open source software is very well established. It's everywhere. I mean, that's a battle that was won some time ago. Every phone contains vast amounts of open source software, even if it's an iOS phone. Android is an open source operating system. And there's open source components, running just about everything from space missions to the world's top 500 supercomputers to tiny little Internet of Things devices. And there's a lot of money in it as well. It is has a huge effect on the economy of countries, and we can go into the reasons for that. So this is one of the reasons that the European Commission a couple of years ago wanted to commission a report on open source software and hardware, the state in the European Union, to look at innovation and competitiveness, and to determine what sort of policies should be put into place in order to stimulate that. And I was very lucky to be asked to be involved in that project, and I was leading the open hardware section of that. Now, I spent some time earlier talking about the extent to which certain types of open hardware, so for example, the development of open silicon, are very similar in many ways to the development processes that exist and have been found to be very successful in terms of open source software. So what we have here is a spectrum of open source hardware that is very similar to open source software, and we are calling that a high degree of softwareness. And then I mentioned dump truck before, which is something that has a high degree of hardwareness. Now, there are quite a few policy recommendations around open source software, and our view was that to the extent that open source hardware is at the software end of the scale, then a lot of those policy recommendations would overlap, and these include things like the establishment of a network of open source program offices, for example, which can be equally applicable to open source software and open source hardware. So one of the areas where open source hardware wins over open source software is that open source hardware does not currently have the problem with license proliferation that open source software does. With open source software, there are many hundreds of different licenses which are attached to pieces of open source code, and tracking those licenses, determining whether they're compatible or not, etc., it proves to be a fairly complex process. Life would be much more straightforward if there was one of a small number of licenses that was attached to open source code. In the world of open hardware, there is a very small number of specific open hardware licenses, and the ones that are most commonly available out in the wild are the SolderPad license, the Tapper license, and the 3 variants of the CERN open hardware license. Having said that, many people do attempt to use open source software licenses when they are releasing open source hardware, and sometimes they also use content licenses as well, like the Creative Commons licenses. Those are not ideal, and it's much more likely that you'll get a satisfactory result if you use a license which has been specifically tailored for open source hardware. So I've been involved in the SolderPad license and also the CERN open hardware license. The SolderPad license is a very straightforward license. It's based on Apache 2.0, which is a very well understood open source software license, and in fact is pretty well suited to hardware as it stands, apart from the fact that some of the terminology is a little confusing. You can't really apply it to open hardware particularly well. So what I did was really modify some of the terminology and also expand the range of intellectual property rights that are covered to cover a broader range, including things like database right, mask rights, and so on, which could be applicable to hardware as well. But other than that, it is very, very similar to the Apache license. The CERN open hardware license, I was involved in that as a member of the core drafting team, along with Javier Serrano and Miriam Ayas, both of whom are from CERN. And that started out life as a reciprocal or copyleft license, but it became clear that it would be most beneficial to the open source hardware community if there were three variants of the license. One variant which is permissive license, which is similar to the SolderPad license and therefore the Apache license, and then two reciprocal licenses. And I won't go into detail now as to why we needed two different ones, but essentially they are to to recognize the realities of development of open silicon. As we've identified before, open silicon is complicated by the fact that the tool chains are very often proprietary, which means that in order to get anywhere, the reality is that you'll have to incorporate some form of proprietary IP blocks and code into the silicon that you're designing. That makes life quite difficult for reciprocal licensing. So we went to great lengths to develop a weaker and a stronger version of the reciprocal license. And the weaker one in particular is designed to be easier to use in circumstances where you're essentially forced to use proprietary tool chains. I would suggest, if possible, using one of the three variants of the CERN Open Hardware license. And the reason for that is that, first of all, you should be able to find the license that you want out of those three. You shouldn't have any other particular concerns unless they're very unusual. Those should cover most of the major use cases. And it makes it a lot easier to create an ecosystem of designs where people are able to mix and match components under the various licenses, and they understand what the relevant license is that they need to use when they are licensing out the whole of the design that's combined, when you've got combined components. So that's one reason for doing that. Another reason is that the CERN Open Hardware license is the only purpose-designed open hardware license that is approved as an open source license by the Open Source Initiative. So we're quite proud of this achievement. It means that the suite of licenses has been through some pretty intense scrutiny by the Open Source Initiative. They have analysed the licenses, determined that each of them complies with all of the criteria contained within the open source definition. And that makes it a lot easier for the license to use. It also means that it's because of the rules of organizations like GitHub and GitLab, it becomes part of one of the sort of drop-down list licenses that are in their license selection tool as well. So it's a much easier choice. And I do get asked from time to time, whether it's a good idea to choose an OSI approved license. And the answer to that is yes, if possible, do that. Even though SolderPad might be an appropriate license to use if you're combining hardware with some sort of Apache software license project, if you've got a permissively licensed project that doesn't fall within that classification, then the best thing to do is to choose the permissive variant of the CERN Open Hardware license.